Hello and welcome back. Today we will be talking about population variance. All right, some key vocabulary before we get started. Population is the entire group being studied. The mean, which we will see denoted with this symbol called mu. I'm not really too sure how to spell it, but it's kind of pronounced like the Pokemon. You know, Mewtwo, Mew, Mew, something like that. Let's get rid of that. Anyway, so the mean, which for population variance is referred to as with this symbol mu here, is the average of the population, which we should know by now. The mean average is calculated by all of the elements of a data set, which we've been referring to as observations, divided by the number of observations. Deviation, the distance between a data value and the mean, okay? In later videos, we're going to go into standard deviation, a super important topic in statistics. Squared deviation, a deviation multiplied by itself. Okay, so why do we square deviations? If we simply add deviations from the mean, the positive and negative values would cancel each other out. Squaring each deviation makes each value positive and gives greater weight to observations that are further from the mean. So essentially we square them just because sometimes we could have negative values. We square them to keep everything positive, which makes our work more easy. Okay. And population variance, which we'll be discussing. This is the symbol we denote for population variance. I'm not sure what this is called. Our population variance symbol. I don't know what the Greek letter is, but the average of the squared deviations from the population mean, okay? So here's our formula for population variance. It looks a little intimidating. This is a new symbol we probably haven't seen before, but we're going to break it down and make it very easy, okay? So here's the definition of all of our symbols here. This guy right here is our population variance. And again, we square it so that it's positive. This guy right here, I think that's the Greek capital letter epsilon. This is the summation notation. It just means sum of. It means we're going to be adding a bunch of things, okay? X sub I, each data value. And there's a reason we have the sub I here, which we will get to shortly, minus mu, which is our population mean, all divided by n, the number of values or observations in the population. Okay. All right. So again, might look a little spooky. We're going to break it down nice and simply. Here's an example. Okay. So our data set, our observations are 2, 4, 6, 8, 10. So you see here, I label them x sub 1, x sub 2, x sub 3, x sub 4, and x sub 5. That's what we mean by the sub I here. The I represents a number, and that number represents which each data value it corresponds to, okay? So x sub 1 corresponds to data value 2, which I also have here. X sub 2 corresponds to 4, x sub 3, 6, x sub 4, 8, and x sub 5, 10, okay? And this is just stuff that's given to us before we even begin. And n equals 5 because we have 1, 2, 3, 4, 5 observations, okay? And over here, I'm going to continue to just have the equation written, and I'm highlighting the part we're focusing on at first, okay? So we haven't even started yet. This is just what's given to us. All we know are the 5 observations, which tells us each x sub I, and it tells us n for 5, okay? So step 1, find the mean, which is mu, okay? So that's this part right here. I'm going to continue using the notation given so we can get more comfortable with it. Mu is defined as the summation of all of our x elements divided by n, the number of elements. So again, summation just means we add stuff. We add x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, add all these divided by n. We replace what each x sub element stands for, 2, 4, 6, 8, 10. Add them all up, get 30. Divided by 5 is 6. Our mean mu is 6, okay? Step 2, find each deviation, which is x sub I minus our mean, which is now this part of the equation we're focusing with. So we just take each element, each observation given to us, and subtract it from the mean we found in the previous step. X sub 1 minus mu is 2 minus 6, negative 4. X sub 2 minus mu is 4 minus 6, negative 2. X sub 3 minus mu is 6 minus 6, 0. X sub 4 minus mu is 8 minus 6, 2. And x sub 5 minus mu is 10 minus 6, 4. Okay? And that's this part of the equation as we break it down. Step 3, square each standard deviation. So now we're in this part of the equation. We haven't gotten to the summation yet. Now we got to square all the things we did in our previous step 2 here. So I'm not going to continue reading everything, but the first part squared gives us negative 4 squared, 16. The second one is negative 2 squared, 4. Third, 0 squared, 0. Fourth, 2 squared, 4. And last, 4 squared, 16. So again, we square them all so we can get them all to be positive. Makes it easier for us, or it's what the steps that we need to do as we continue. Okay, step 4, add the squared deviation. So this is the summation part, which I introduced with mu and the mean. So this just means, so now this is this part of the step where we add them all. This just means everything we take from step 3, now we add it all up. So here I wrote out what that looks like with when we just generalize it with our variables, but we already know from step 3 what each one of these little parts equals. And we could say, let's do it, I like green. This is that number, that's that number, that's that number, this is this number. Oops, oh, I'm off here. Let's fix this. This should be, there we go. This is that number, this is that one, this is that one, this is, the 4 there. And actually, let's stay consistent. This is that one there, and then this is our 16, okay? And again, we derived all these from the previous step, but just showing the summation means we add up all of the values that we calculate in our last step, okay? And when we add them all up, we see here, the new value we get is 40. 16 plus 4 is 20, 4 plus 16 is 20, 20 plus 20 is 40, 0 does nothing. All right, so that's this step here. And our last step, divide by the total number of observations, our n. We already determined it was a given, n equals 5. 40 divided by 5 is 8. So our population variance is 8 square units. And it's square because we define it to be, okay? Again, it looks trickier than it is. It's pretty simple. All right, interpreting population variance. So what does this information mean? A larger variance means the data are more spread out. So the bigger this number is, the more the observations in our data set are separate from each other. A smaller variance means the data are clustered closer to the mean. Because variance is measured in square units, it's often difficult to interpret directly. This motivates taking the square root to observe standard deviation, which the standard deviation is an extremely important subtopic in statistics. This will be addressed in a later video. All right. Real-world applications of population variance, manufacturing quality control, test score consistency, investment risk, weather measurements, and scientific experiments. And then common mistakes we see, forgetting to subtract the mean first. That's referring to step 2 here. We have to subtract the mean from all of our observations. That's a common mistake. Forgetting to square every deviation over here. Once we do our subtraction, you have to square that number. All of our numbers should be positive. If anything in our last couple of steps, if we see any negatives, we know we made a mistake. Dividing by the wrong denominator, divide by the number of observations. Confusing variance with standard deviation, 2 different things. Again, this will be addressed in a later video. And forgetting variance is measured in squared units. Whatever your variance is, the unit should always be squared. All right, and let's do a practice problem. Here we have 3 questions. Question 1, find the population variance of 5555. Question 2, find the population variance of 357911. And 3, which data set has a larger population variance? Before you pause, I just want to make a comment here. You can notice the notation I used for the observations. these are brackets. We use brackets in mathematics when talking about a set of observations or elements. Going forward, you will see me use this more often, but I just want to introduce and just let you know that all these brackets mean is like, hey, these are the elements of the set that we're going to be talking about. Okay. Anyway, feel free to pause here and take a stab at these. All right, let's take a look. So the first one here, we don't really even need to do much work. I showed it out anyway, but because all of our observations are the same exact number, our average is going to be that number. 5 plus 5 plus 5 plus 5 is 20, divided by 4, which is how many we have, you get 5. So when we do our subtraction, we're going to have 0, and our population variance is simply going to be 0. And we also know just from looking at it, there is no variation of the observations because it's all the same. There's not going to be any distance from the mean because the observation itself is the mean. So our first answer, we should have gotten 0. Again, I just drew out the work. You can just look at it and see. 2 is a different story. So 2, we have 3, 5, 7, 9, 11. Okay. We have 5 elements, 1, 2, 3, 4, 5. So n is 5. And when we calculate the average of these, it's going to be 7. Now, we could also see because it just simply increases by 2 from the starting point, plus 2, plus 2, plus 2, plus 2. Our average is the same thing as our median, 7. But if we add all these up, divided by 5, we will still get 7. Okay. Then we take each element, subtract the average from it, and square it. We should get 16, 4, 0, 4, and 16. And then we add all those up and divide by the number of elements. They add up to 40. 40 divided by 5 is 8. Which you should notice that this is the same answer as our practice problem, also 8. And the reason it's the same answer is because this step, at step 4, we got the same numbers here. And the reason we got the same numbers there is because we went up by the same thing, just increased by 2. Plus 2, plus 2, plus 2, plus 2. And we just started one number off, so it's going to give us the same results. And which data set is a larger population variance? Again, for the reason that number 1 is 0, we don't even need to do the work. We could see that this is all the same number. These numbers increase by 2. We should know just from looking at this, our population variance is going to be 0. And this one, let's see what that, I didn't even do the work. I just looked at it and was like, hey, I already know this is 0. This one's going to be greater, easy peasy. And that's population variance. Again, I know the equation can look a little spooky if you're not used to seeing summation notation, this guy here. If you're not used to seeing this, it can be a little intimidating, but hopefully I broke it down to make it a little simpler for you. But that's everything I have for you on population variance. Thank you for tuning in. As always, these notes will be in the video description, and I will see you next time. Take care.